Hey, AK again. In this video, we are trying to answer the questions: what actually is this Matlab software, and what is Matlab being used for in the real world? And here's my take on that. Matlab is a software that is used for modeling physical, engineering, biological, and financial systems, and also for analyzing and plotting large data sets using matrix math. Let's start with the modeling part first. Let's start with an example of a system modeling from physics. I'm going to talk about the propagation of electrical and magnetic fields, or in short, electromagnetic fields in space by using the following famous Maxwell's third equation. This is the Maxwell's third equation in differential form. We read this as this inverted triangle followed by a multiplication sign as the curl. So we read this as the curl of this electric field. This E is the vector electric field and B is the vector magnetic field. So we say the curl of the electric field is the negative of the partial derivative of the magnetic field with respect to t. Also remember, both E, the electric field, and B, the magnetic field, they are functions of both the time and space. So we can model this equation in Matlab, and we can actually plot the distribution of electric and magnetic fields, in short, electromagnetic fields in space. Fire up Matlab, go to folder number 7 and load up the script called what is Matlab used for. The actual physics application starts here, Maxwell's third equation in point and differential form, and we're going to solve this equation in Matlab, and we're going to plot the distribution of the electromagnetic field in space. So three-dimensional space, electric field, magnetic field. All right. Okay, we are looking at an engineering application in Matlab. Imagine a tall building which is being subjected to an earthquake, and the response of this tall building we are going to model in Matlab, and I'm going to show how it's usually done by earthquake and civil engineers. So the acceleration due to the earthquake, it can be easily measured with sensors, and the building is actually modeled as a set of connected masses, masses connected by springs, and we can create a model for this mass and spring system using the second order differential equation, md square x by dt square plus kx equals a of t, where m is the mass matrix. It is the matrix of all the nodal masses, and x is of course the node displacements, so it contains the displacements for all of these nodes, and k is the stiffness matrix for the springs that are actually connecting these nodal masses, and a is the acceleration vector, that is the input stimulus. And we have talked about differential equations like this, in the previous videos. So we use similar techniques, and we actually solve for the displacement of these nodal masses. Now I'm going to talk about an application in biology for Matlab, and let's actually talk about an ecosystem where we have predators and prey. Say for example wolves and deer. Predators and prey populations are interdependent. Wolves actually start eating too much of deer, the wolves population go down, the deer population shoots up, the wolves start eating the deer, then the wolves population actually shoot up. So they're both cyclic, they actually go up and down in cycles. And the math model for such a system is this set of these two nonlinear differential equations. X is the predator population and Y is the prey population. Alpha and beta actually the constants, the empirical constants. And notice that the variables of interest X and Y, they're actually being multiplied on the right hand side. That is why this is a nonlinear differential equation. This is the famous nonlinear differential equation in mathematical biology called the Volterra-Lotka equation, and we will solve this Volterra-Lotka nonlinear differential equation in Matlab like so. You go to the section for the biology application, left click anywhere here and press Ctrl Enter, and Matlab actually uses the techniques that we discussed in the previous videos and solves this nonlinear differential equation using numerical techniques. And this is the plot of the prey the deer population with respect to time, and this is the population of the predators, the wolves, with respect to time. This is a neat example of a MATLAB application for a biology problem. Moving on, we are considering an example from financial engineering or econometrics, and I have actually taken the S&P index for an arbitrary number of days. It really doesn't matter. I just took some arbitrary number of days and I plotted the stock price movement. So we are going to talk about mathematical methods in MATLAB that can be used for predicting the stock price a little bit ahead, in future. So the way to do that is you bring this stock data into MATLAB as a discrete sequence. So this is a discrete signal sequence, and we test for stationarity. This is a statistical test, and the discussion of test for stationarity is actually beyond the scope of this video, but know that sophisticated methods actually exist, and we can use them in MATLAB to do the statistical test. And once we are satisfied that the condition for stationarity is fulfilled, we can model the whole stock movement as an ARMA process. ARMA here stands for auto-regressive moving average process, and the discrete equation for an ARMA process is given like this. And we use techniques and theory from digital signal processing and linear systems analysis, and we actually predict the future movement of the stock using the techniques that I described above, and we can actually predict a little bit ahead in future. Okay, now we are coming to the data analysis part. In MATLAB, we can easily read in relatively large data sets and do pretty advanced math on the input data set. As an example, say you're doing some image processing on a series of images from a CT scan of the brain. So you take in an image, or rather a series of images, and one image actually looks like this, and you are capturing dozens, tens, sometimes hundreds of images for analysis. And the way you would do data analysis on this image set is as follows. The first image is 1024 by 1024, say, and the second, third, etc., up to image 100. So this set of images is actually represented as a 3D matrix in MATLAB, and the data structure is something like this. It has 100 pages. Each page represents one image, which is 1024 by 1024. All right, so we can do lots of sophisticated math operations on this 3D matrix data set. We can, for example, do averaging, we can run edge detection algorithms, and we can do 2D fast Fourier transforms on the data set, and many other operations. So it is just one example of processing large data sets in MATLAB efficiently. Okay. Coming to the plotting part, MATLAB can produce simple line charts, multiple plots in the same figure, three-dimensional plots, say vector flow field diagrams of a gas flow or the exhaust of a jet engine, for example, histogram plots, polar plots, antenna signal strength diagrams, for example, 2D and 3D heat maps, pie charts, etc., just to name a few. In short, if you have the math model for the system that you're working on, MATLAB can probably simulate it. Also, MATLAB has pretty decent capabilities when it comes to handling large input data sizes, unless we are talking about matrices that are in the range of 100,000 by 100,000 elements. Okay, then it's probably time to go to Python. When it comes to plotting, MATLAB has superb capabilities. It can produce pretty much any plot that you can think of. Okay, that's it. Thanks for following this series called 1 Hour MATLAB so far. I hope this has been useful and interesting. Please leave your comments and feedback. Good luck with your MATLAB journey. Thanks for watching.